Good morning. Today I'm going to talk about a new application for our Elika pump. But first, a brief introduction. Gear pumps are great. Marzocchi has been manufacturing gear pump for many years. These type of pump are small, lightweight. They can provide high flows with high pressure. The only problem with this pump is as the pressure and the speed rise, then the noise becomes intrusive. Many of the new applications that we are approached demand for low noise pumps and appliances. So Marzocchi went on trying to understand where the noise comes from. Turns out that the noise comes from most of the noise comes from the encapsulation of the oil between the teeth. In that small vein, the oil gets trapped, compressed, and then makes noise at every engagement of the gear. So we went on designing something that could solve this issue. In fact, as you see in this slide, the two pictures below show the traditional spur gears on the left, and on the right, the new profile of the Elika gear. So, as you see, there is no space for the oil to get trapped between the gear teeth and the vanes, because the two profiles are exactly matching each other, completely closing the gap between the tip of the teeth and the vane on the other gear. So this allows the pump to get rid of the noise, the hydromechanical noise coming from that encapsulation. The helical gear also has a low number of teeth. This low number of teeth allows the pump to move the noise of the pump towards a lower frequency range, and also to reduce the frequency of the pressure ripple. We designed our Elika pump to be interchangeable with our production. So as you see from the picture, from the outside, the Elika pump looks very similar to a standard gear pump. The difference, though, are inside. Of course, the helical gear and the particular shape of the teeth is one. But because of this gear, there are other problems that had to be solved before having a pump ready for production. One of the main problems is the thrust that's generated by the pressure and the torque on the gear. This thrust is axial, and as you know, gear pumps have a tendency not to like very much axial thrust. So even more difficult is that part of the thrust comes from the pressure and pushes both gears towards the back, so towards the cover, the rear cover. But the component that's due to the torque transmission actually pull the drive gear towards the back and pushes the idler gear towards the front. So when you add up these forces, they're not equal. In fact, the idler gear is subject to less thrust towards the back than it is the drive gear. For this reason, we needed to design a compensation for this thrust that would cancel the two forces on each gear. And because of this, what we decided to do was to take the pressure from the outlet of the pump, from the pressure side of the pump, and feed that behind two cylinders. And varying the diameter of the cylinders would provide the force that we needed to counterbalance the idler and the drive gear forces. So in this picture, you can see the channel that's machined into the cover that takes the pressure from the outlet area of the pump and feeds that same pressure behind the cylinder, behind each of the two cylinders. And those two cylinders generate the force that's needed to counterbalance the gears. So now the gears are perfectly balanced and don't push on the bushings itself. So in this picture, you can see the whole range of Elika pump that we now have in production. They are divided into 5 groups, and they range from 2.1 cc all the way to 200 cc. All of them share the same design. Smaller groups like Eli1P and Eli1 are used in the automotive business, like cars and trucks, while bigger pumps like Eli2 and Eli3 can be used on forklifts, and Eli3 and Eli4 are also used for bigger machinery like telehandlers. Now in this picture you can see the overall efficiency of an Elika pump. Now the Elika pump was designed specifically to be low noise, but once we got the pump on test, we figured that this pump was also capable of maintaining a very high efficiency at low speed, which is another issue that gear pumps tend to have. So this pump was capable of spanning speeds of 250 RPM all the way to 5,000 RPM. So with this type of pump, what we could do actually was, with the single fixed displacement pump, achieve a wide range of flow by just changing the speed. For example, the picture shows a 3.7 cc pump ranging from as low as 1 liter per minute all the way up to close to 20 liter per minute. So this gave us the idea that we could use this pump in combination with a variable speed motor, so a brushless motor, to effectively design a motor pump combination that could be used as a variable displacement pump. It's just producing variable flow. This was particularly targeted to electrical vehicle application, because in those vehicles there is no noise from the internal combustion engine, and so any other noise on the vehicle becomes apparent. So everything needs to be made quiet for this type of vehicle. So the first pump we designed, and you can see the picture here of the first prototype, completely machined, was this 3.7 cc pump that was 100% compatible with our K1P line, so our standard straight gear pump. And we coupled that with the brushless motor. So when we tested this combination, this is what we found. Now first, we tested the pump itself alone, detached from the motor. On our test benches, we could see that the volumetric efficiency of this pump remained above 90%, even as low as 250 RPM. And we could go all the way up to 5,000 RPM, full pressure, and achieve very high efficiencies. Mechanical efficiency was very high as well. Of course, lower pressure had lower mechanical efficiency, but you can see from the picture that mechanical efficiency stays above 70% for all conditions and above 80% for higher pressures. Of course, we needed to compare the noise of this pump with a standard pump, and what we found was that the Elika pump, for the whole range of speed that was capable of, stayed below the 60 dBA. While to reach the 60 dBA on a standard pump, you just need to run about 2,000 RPM, and you're already over 60 dBA. So the standard pump at 5,000 RPM was like as loud as 80 dBA. So this graph shows just this. The average noise comparison between the Elika and the K1P, same displacement. What you see is that the Elika not only is more quiet, but also the noise increases less steep. One particular aspect of the noise of this pump is its frequency. You can see in this picture the frequency spectrum taken at 1500 RPM comparison between the Elika pump and the standard gear pump. The Elika pump in green shows the frequency spectrum shifted towards the left, so towards the lower frequencies. The lower frequency spectrum means that the noise is more pleasant. A standard gear pump has a pitch on a high frequency, which is particularly unpleasant to hear. When we move to 3000 RPM, we see the same thing. The standard gear pump has peaks on the high frequencies, whereas the peak of the Elika pump is towards the middle of the graph, towards the frequency that are more pleasant, lower frequency. So not only is the sound pressure less, but also the noise is more pleasant. So in this picture, you can see the influence of pressure on the noise of the Elika pump. Basically, going from 5 to 150 bars, there are very limited differences between these two pressures. So that means that throughout the whole range of pressure and speed, the Elika noise is consistently low. Another thing that's important on today's machinery is the pressure ripple. That causes vibration, and those vibrations are transmitted to the vehicle. You can see from this picture that the Elika pump has, of course, lower amplitude on those pressure ripple, but also lower frequency as compared to the standard gear pump, which has higher frequency and also higher amplitude of the ripple. This picture shows a summary of what I just said throughout the whole range of pressures. The pressure ripple of the pump, as the pressure increases, becomes a lot different between the two pumps. And the Elika pump is consistently lower than 0.5 bars. So now we add the motor to the picture and see what happens. In this graph, the first thing we plotted was the current versus the flow. So this shows how the motor pump combination works. Different pressure, what current is needed to achieve what flow. Of course, the graph you can see is limited on the upper part by the 160 amps of the motor, and on the right, it's limited by the maximum flow that the pump is capable of providing. Going to efficiencies, this graph shows the overall efficiency of the system. So the pump plus the motor, and this efficiency is calculated by taking the hydraulic power out of the pump, so pressure and flow, and divided by the power, the electrical power inputted to the motor, so voltage times current. You can see that at the design point of this pump, the efficiencies are in the range of the 60–70%. Now the combined noise of the pump plus the motor, you can see from this picture the motor alone in red throughout the whole range of speed that the pump motor combination is capable to provide. Now this shows that the pump adds just a tiny bit of noise over the motor, which is already very silent. So all the way to 150 bars, you can see that the pump just adds 3 to 5 dBA. So this is a very small amount of noise added by the pump, and in any case, the whole combination, pump plus motor, always stays below the 60 dBA, which is a very good target. As far as frequency spectrum of this combination, you can see on this graph the motor alone in red and the motor plus pump in green. As you can see, the lower frequencies are just about the same. The pump doesn't add anything to the motor, so the pump is less noisy than the motor itself. So where the pump introduces more noise with respect to the motor is on a higher spectrum, where we know the Elika is very silent in the first place. So as you can see, you can see figures of 30, 20 dBA, which is a very low noise. It's similar to an anechoic chamber. So it's close to the baseline of measurements. So overall, again, the whole combination produces a peak of a little bit less than 60 dBA altogether. So in the end, using this pump for this new application, even though it was designed for low noise, this way the pump behaves at low speed allowed us to see new fields of application. And actually, we had requests for this type of pump motor combination. And the advantages of this is the possibility, of course, of obtaining variable flow from a fixed displacement pump. So a pump that's more economical with respect to a variable displacement pump, and is also capable of achieving, by just controlling the motor with the electronics, flow ranges that are like 20 times the ratio of the maximum and the minimum flow is like 20. So that's huge for a gear pump. Also, the efficiencies of this combination are such that the pump is particularly suited for electrical vehicles where, of course, power consumption is critical. Another advantage of being of consuming less power is that the heat introduced on the system by the losses of this system are less. And this means that you can reduce the size of the reservoir, and then of course reduce the size of the heat exchanger. So everything becomes more compact. And of course, the inherent advantage of the Elika is the low noise. So the whole package becomes more efficient, smaller, and less noisy. So that's what we think is the right product for the future vehicles that are going towards the electrification. Thank you.